This floating point addition or the floating point arithmetic, it is also to be discussed in chapter number 3, unit number 3, as per the prescribed syllabus. Before we understand the floating point addition, floating point representation, there are two different techniques, FPO, floating point operations. One is the American standard, American national standard, and we have IEEE 754. So we have seen the IEEE 754 representation format. In this, we have single precision, which is of 32-bit, and double precision, which is 64-bit representation. So we stick our discussion to single bit. The only change is the number of the Mantissa part will be more and the exponent part will be more in the double precision. So as per the IEEE 754 format, so I am going to discuss IEEE 754. So do not get confused with the textbook which describes ANSI format. So we are going to discuss both. So IEEE 754, this 32-bit single precision, it has three components: sine component, sine, exponent, and Mantissa part. And the size of this sine is 1 bit, this being 8 bit, and the remaining 23 bit, it is reserved for the Mantissa. So that was the idea. And also you must, before we start converting the, start the floating point addition, so you must be able to convert the fractional decimal into binary also. And what is that number system looks like? So this is integer part side, and this is the decimal part side, that is fractional part side. And these are the place value. I'm going to write the place value at the both the side. So it is 2 raised to 0, 2 raised to 1, 2 raised to 2, 2 raised to 3, 2 raised to 4, and so on. So these are the place value. And for the fractional part also, the place value will become 2 raised to minus 1, 2 raised to minus 1, 2 raised to minus 2, 2 raised to minus 3, 2 raised to minus 4. It goes like this. So if you represent this, so this will become 1, 2, 4, 8 like this. And this will become 0 0.5, 0 0.25, 0 0.125, like this it continues. We will take one example. Say for example, I will take 5.75. This is in decimal, and we must be able to convert into binary. So draw the number system 1, 2, 4, 8, and the place value for this is 0.5, 0.25, 0, 125, okay, and so on. So I need to make it 5. So make it 5. So I don't require this 8. So 4 I require 101. So 4 plus 1 is 5. And I need to make 0.75 out of 0.75, 0.5, yes, I need it. And 0.25 also I need it, and the job is done. So this 2 is 0.75. And this turns out to be 5. So the equivalent binary number will be 101 dot decimal point 110. So the 0 backside won't represent anything. So the answer is 101.11 to the base 2. So this was our IEEE 754 Now this is 1 to the base 2. Okay. Now actually here we did mistake. Yeah, I got it. Now here what we have done is, if you look at this decimal point, so I have shifted 2 times. So but I want in 1 dot Mantissa format, 1 dot Mantissa, not 0 dot Mantissa. So I need to make the decimal adjustment for 1 dot Mantissa, but we have done with 0 dot Mantissa. Okay, so this is wrong. So I need to do actually this into 1.11. And how many decimal points we have shifted? 2 raised to 1. 2 raised to 1. Okay. So remember, it should not be in 0 dot Mantissa. It should be 1 dot Mantissa, because the expression says 1 minus 1 raised to sine 2 raised to exponent minus 127 1 dot Mantissa. Okay. So you need to put in this format 1 dot Mantissa format. Now what is exponent? This is plus. So sine is 0, exponent is 1, right? And you need to add the bias exponent. Okay. So that will become 128, 127. So 128 bias exponent. So put this, and Mantissa will be so 0.11 and so on, all zeros. Now we are going to put in terms of sine bit. So sine is 0, Mantissa is 128. So 1,000,000 4 zeros. Okay. And sorry, this is exponent, bias exponent. And Mantissa is 1100 and so on up to this. Now you can convert this into hexadecimal. This is 4, this is 0, and this is 600, like that. Okay. So all this will become 0 to the base 16. Sorry, to the base 16, but it is in Ieee 754 is 0. And what about 2 raised to e minus 127 1 dot Mantissa? That is Mantissa is, yes.
4060, sir. It's the middle four is
Sorry, yeah, sorry, 4060. Okay. And Mantissa is how much? 8 bit. If you see it, Mantissa is 128. So minus 1 raised to 0, 2 raised to 128 minus 127, 1 dot Mantissa. So this is 1, 2 raised to 1, 1.11. So 1 into 2 raised to 1, so 1 dot. So convert this 1, 0.11. This is 0.5, this is 0.25. So it is 0.75. So 0.75. 1 into 2 raised to 1 is 2 multiplied by 1.75. Now this is 3.5. So we are correct. Now I will take one negative number, that is minus something like 17.625. I will take this number. Now you also start doing with me. Now this is in decimal. So you need to convert into Ieee 754 single precision, that is 32 bit. Single precision 32 bit. Okay. Take just ignore the sign as of now. We will deal with the sign separately. Now you take 17.625 to the base 10. Now can anybody answer what is its binary equivalent? Binary equivalent. So how to do this one? This is your decimal point. Place values are 1, 2, 4, 8, 16. And this is 0.5, 0.25, 0.125, and so on it is. I need to make it 17. So 1,
17, 0,
0,
0,
0,
0,
1, and 6.25. 0.625.
1, 0, 1.
So 1, 0, 1. Okay. So if you add 0.5 with 0.125, you will get 0.625. Okay. So finally we got 1,000,1 dot 101 to the base 2. So this is our step number 1. So the given decimal number needs to be converted into binary. Ignore sign initially. Ignore sign initially. Now what we are going to do? Adjust this decimal point.
2 power 5
Adjust this decimal point
towards left.
towards left, but remember in which format? One dot format. Okay.
Yep.
So if you do it as I did first time, that was wrong, right? So 1, 2, 3, 4. If you do 5 times, then you're gone wrong. So it should be one dot format. So 1, 2, 3, 4. So 1 dot 0, 0, 0, 1, 1, 0, 1 into 2 raised to
4.
4. Okay. Do not put in 0 dot that format. Please take precautions. Okay. So it should be in one dot format. Okay. Now, what is next? What is next step now?
Take the S as 1 minus.
First exponent you need to take
4 plus
4. Now add the bias value. What is the bias value for 32-bit?
127.
127.
127.
And this turns out to be
127.
131. Now, what is next step after this?
Convert into binary number.
96.
Binary number. Okay, good. So I need to
96.
convert this 131 into binary. So I will write 1, 2, 4, 8, 16, 32, 64, 128. This 128 is done. Now
2 and
this,
1.
this. Okay. So the 1,000,000,000,1. So it is equivalent to 131. Now we are going to write sine, exponent, Mantissa. So what is sine?
1.
It is minus, right? Sine is
1.
minus. So we are going to write 1.
Yeah.
Okay. What is biased exponent?
100000011.
1,000,000,011.
Yeah.
And what is Mantissa? Look at this. Mantissa.
Double.
Okay. 1,000,000,11,01.
000.
Yeah, 000.
Double one
After
zero
this,
one.
0,000,11,01. And you need to continue this till the size becomes 23-bit. Okay. So rest are all zeros. Fine. So if I want to convert into hexadecimal format, so this is no binary. So I can club all together. It appears like this: 1100
Zero zero zero
0001 1000. Then this is 1101, and all rest are all zeros. Okay. If I want to put into hexadecimal format, this is 8 plus 4, right? 1248. 8 plus 4. It is 12. And how to write 12 in hexadecimal? It is C.
C.
Okay,
C.
and this is 1,
C.
and this is
8. 8.
8,
1.
and this is 8 plus 4,
D.
12. It is D, and rest 0. Again, it will come 0, 0. Totally 8 digits you need to write, because each hexadecimal digit is 4. 1, 2, 3, 4, 5, 6, 7, and 8. So this is finally your IEEE 754 in 32-bit format.